Thank you for coming. So we have a presentation about graph theory, so let's start with a short story. I don't know if you already heard about the International Consortium of Investigative Journalists. It's basically 200 journalists collaborating on investigations. It's a non-profit organization, and 2 years ago, they received a giant leak of more than 11 million of documents from a very small Panamanian law firm, Mossack Fonseca, and these were the so-called Panama Papers. It involved more than 200,000 offshore entities, and the documents were dating back to the 70s. So they were really having 40 years of internal documents of Mossack Fonseca. It was the very, very first time that such a massive leak occurred. Just to realize, the number of documents is 4 times larger than the Snowden leak, for instance. Another issue was that most of the information they received was unstructured data. Half of them were emails. They also received images, PDFs, and some databases with, of course, no dictionary of variables or something. So the question was how to make sense of these 2 terabytes of data. There are only 200 journalists, so they had to find something because it would be a never-ending process to analyze all this information and try to make sense of it. So their research office suggested an idea. They could analyze all these documents with a network perspective. Every journalist that would read a document could record the entity, the client, the companies, or whatever the type of entity in a unified database. They could also record all the links. For instance, even the same family is a shareholder, and all types of links they could think about with this 200,000 offshore entities plus persons, plus law firms, and so on. They did that using a graph-oriented database, a NoSQL database named Neo4j, and they really recorded all the types of entities they thought about, so clients, companies, officers. And after that, they used a specialized database software, Linkerus. So once the graph database was built, they were able to analyze the network easily and identify connected groups of peoples, and eventually identify abnormal transactions and all the scandals we heard about later on. It allowed to publish many articles on, in various countries and at various decades, and it really allowed this technical framework, so a graph-oriented database, network analysis, and specific database software to make sense of these 2 terabytes of information. And with Alberto, we are here with you today because we are really enthusiastic about these types of analysis, and we really think that it can be useful for you in a variety of situations. That's why we are going to show you the tools we think are really interesting.
Okay. So the title of this talk is Looking for Communities and Finding the Leaders. These are just a couple of examples of what we can do on graphs. There are a lot of possible use cases we are going to discuss a little bit. But first of all, the first question is, what is a graph and why should we care about it? The idea of a graph is very simple. It consists in studying a system just in terms of its nodes, its elements, and the interconnections existing that are called sometimes links. The question is, are there a lot of systems that are just that can be described just by looking at the elements and the interconnections? The answer is no, because there are always a lot more characteristics that one can look at when analyzing a system. But nevertheless, there are some situations in which we have no other choice. The Panama Papers is a very good example. We don't know what to do about all the amount of information that we have, and so the graph theory can help us in making some sense about our data, about our system, and then of course we can also decide to apply other approaches in order to study more in details the real characteristic of the graphs. Who we are? We are both consultants at Quantmetry. It's a data science consulting firm based here in Paris. We are now about 70 consultants with very different profiles, and we work for several clients, several businesses, and in several phases of data science, data architecture, and data engineering projects. And we have also some time to study some R&D subjects, and it was mainly in this scenario that we had the opportunity of studying these graph approaches. As I was saying, a graph is just a structure made up of nodes and links. On the right hand, you have a nice example. It's a transportation network. In this case, also, I mean, this is not at all a real representation of the subway systems, because the distance are not at all the real ones. Also, I mean, here you have some straight lines that in reality are not at all straight, but who cares? I mean, in the end, we are just interested in knowing how many stops we have to do and in which point we can change the line. So in this case, the graph representation, even if it's not at all representative of the reality, it does the job, and it's completely efficient and in order to solve our problems. And this is the case. This is often the case in many situations. The information we are losing, it's not so important to us. Just before talking about the two main subjects, these are 4 examples of what we can do when looking at the graph. So there are the problem of the spreading. We can have on a network, we can have something that is spreading, and we may be interested in accelerating it if we are thinking about a marketing campaign, or we can be interested in stopping it, and this is, for instance, a vaccination campaign. In this case, just the graph structure is enough in order to understand a lot about the dynamics of the spreading. Then there are domino effects. For instance, this is applied to economics in order to predict crisis. In 2008, the probability of having multiple failures of big banks was considered completely negligible. But this was not the case, because indeed there were a lot of interactions between different banks, and so what was considered almost impossible, it happened. And a bit more an analysis made with graph theory could have helped in order to understand this possibility. Then there is dynamics. For instance, one of the oldest problems in graph theory is, what should I do in order to reach a point B if I am now in point A? It seems an easy problem. It's very, very computationally expensive. It's an NP complete problem if somebody knows about the complexity of this kind of problems. And then there are some other things one can study. That is, what does it happen if I modify even slightly the structure? Does my path is my path going to be much longer? What is the effect of removing some nodes from the system, and so on? And this is applied also in real world. I mean, if there is a subway stop that is blocked for works, we should be interested in knowing the effects of such a phenomenon on the global behavior of our system. Structural importance, we are going to discuss a little bit more about this, and the idea is in our structure, how can we define structural importance of the nodes? We are just looking at the position and the connections between nodes. Then there are maybe other factors that are defining the importance of one node. But already just looking at the structure, we can define an importance. We are going to look for communities. First of all, again, what is a community? All of us, we have an idea about what a community is. I mean, intuitively, it's some region, some part of, for instance, a social network, in which there are a lot of internal connections. If we consider a group of friends, there are a lot of connection among them, and this number is much higher than the number of connection from the inside to the outside of the group. It's not at all formal, this definition, and indeed there are a lot of possible formal definitions that adapt in some way to this intuitive idea. But the main principles are the same, and there are some questions one can have about these communities. For instance, which are the interaction between them? This is sort of a macro network. Here we have a network with some nodes, and then we create this community, and then we study the network of the communities, because not all the communities are going to interact with each other. And this is another layer of the abstraction one can do that can be interesting. Here we have the network of co-authorships in scientific papers. And what one can look at is the fact that, for instance, the paper about the people working on RNA structure are more likely to collaborate with people working in statistical physics than with people working in mathematical ecology, for instance. So this meta graph can help us understand what's going on. Another topic that is which elements act as bridges between communities. Again, this node is very important, because if we remove this node, then the yellow and the light blue communities are going to be completely separated, and we are, in some sense, breaking the structure of our graph. This is going to come over also in the part when we are going to discuss the importance of nodes. How do we find cluster? There are two main approaches. The first is a top-down approach. The second is a bottom-up. Top-down, we find the bridges. Aurélia is going to discuss a little bit more about what a bridge is in a technical term, but the idea is just a bridge between different communities. In this example, it's quite clear that this central link acts as a bridge between these left and these right communities, and we cut it, and we go on and on interactively up to the point where we construct several separated clusters, and this is the answer of our problems. There are just some example of algorithms having this logic is spectral clustering and Girvan-Newman. The bottom-up approaches are, well, we have a network, we try to gather the elements that are the most connected. And this is completely another class of algorithms, and we have, for instance, fast-grade, the Louvain work trap, that has a completely different logic. Instead of cutting the graph in the most critical parts, we try to put together the nodes that are most similar, most interacting with each other. Two examples of algorithms. For the top-down logics, we have Girvan-Newman. It's a very, very good algorithm with excellent performances and excellent capabilities of finding the clusters, the real clusters. Problem is, as I was saying, this is a very, very tough computational problem, And so this kind of algorithm, finding the bridges, it's very tough. It's very tough just finding one bridge, and we have to do it iteratively many, many times. So in practice, this algorithm is usable just up to some hundreds of nodes. That is not much if we think that we could be interested in finding communities on LinkedIn or on Facebook, but this we are talking about billions of nodes. But even in a much more constrained situation, even with just a couple of thousands of nodes, these algorithms are not going to work very well. On the right hand, we have random walks on a network. This is quite intuitively. A random walker is just a walker taking random steps on our graph by following the links existing. And of course, if there is a region with a lot of links, then the probability of staying inside these clusters is going to be high, because the probability of going out, it's quite small. I mean, we have to jump on exactly one link in order to exit from these right-hand clusters. The communities are then identified as the groups of nodes in which this random walker has the highest probability to stay within, and the strength of the community is described as the probability of staying inside one of such communities. The winner is, we had the opportunity of working with this algorithm in a real world case. According to our experience, Louvain algorithm is very good because it gathers some nice features. It is able to identify heterogeneous communities. That is the case in some scenario. It is efficient on large graph. The complexity is not very high, and so we are able to run community detection on graphs of millions of nodes. And it is available in most analytical libraries. So typically, with a couple of lines of codes in R or in Python, we can already be able to look at the first results, and then, in case, to go further and to try and solve better our problems. It works by maximizing the modularity. That is just a measure of the density of edges inside one cluster with respect to the edges existing outside the clusters. And it is a two-steps. It is a two-steps iterative approach, in the sense that, first of all, we try to reassemble groups of nodes, and then we call these groups clusters, and then we try to reassemble groups of clusters, and so on, and so forward, up to the point where this modularity, this matrix, is no longer improved by gathering communities, because at a certain point we are going to try and put together things that are not very well connected, things that are not a real community. And this is the situation in which we want to stop our algorithms. How do we measure performances? This is typically a non-supervised algorithm because it's really rare to have a real answer. I mean, what are the real communities on Facebook? It depends on what we are looking for. There are two ways algorithms can be tested. The first is, in some very specific cases, we know the communities existing in the networks, and we know a ground truth. This is an example of a very famous example of two groups of people that were at a certain point in the same karate club that split, and by looking at the structure, we can try and identify the two subgroups that are going to be created. The problem is that there are very few existing datasets as this, and moreover, the ground truth can be not so well connected to the structural part. I mean, we can have communities that are not structural, that are not going to be found by these algorithms, but that are due to other aspects of our system. That is really much more complicated than just a list of elements and a list of interconnections. On the right hand, you have a more modern approach that is called stochastic block model, but the idea is I create the truth, I create the communities, and I create the communities that are really structural communities. How so? I define the probability for each couple of nodes to be connected, and in the simple case, I say that the probability is higher if two nodes are defined as being in the same cluster, in the same community, and it is a smaller probability if this is not the case. The effect of having more links inside a community than outside is then just a consequence of this probability structure I am imposing on the system. And two nice features of this approach. The first is that I can study very different things. Here you have two examples, a real community structure and a disassociative structure in which each node has a higher probability to be connected to someone that is in the other community. This is something that exists also. And then we can generate as many observations as we want, because it's just a computational creation, and we can fine-tune the probability and look, say, what if the probability of being connected inside is 50% and outside it's 49%? Maybe it's too small, this difference, and so no algorithm is going to be able to detect the communities. We can try and set the threshold up to which the algorithms are still working and are still able to identify the real answer. Sometimes there is just no pattern to be discovered. This is the truth. I mean, not all the systems have a community structure, so sometimes it's not the fault of the algorithm. There are no communities to be found. The modularity can help us, and also in this case, because it's a value from in the range of -1 + 1, and typically, if this value is smaller than 0.3 in the best solution, it means that there is not really a community structure. Possible causes: the probability, if we are generating our truths, the probability of having links inside and outside are just too close, and so there is no actual difference between the two. On real networks, maybe the known communities do not influence the structure. There are communities, but from a structural point of view, there is almost no difference. Or the approximative solution we are finding, because we are not able to find the perfect solution. It's too tough as a computational problem. We are not able to find the real optimum. And so in some cases, the approximative solution we are finding is just very far away from the global optimum. Possible follow-up. I mean, this is just something you can, an approach you can use, but it can be mixed with other approaches. And there is a nice approach that mixes it with NLP, natural language processing. And the idea is that, okay, we find a group of people, but not just a group of people from a structural point of view, but also in terms of what they are talking about. It has applied to networks in which you have also text, for instance, networks of Twitter, where you have the text of your tweet, or on Facebook, or emails exchanges. And so you have to, you are looking at the structure, but also you are looking at the subject of the discussion, and maybe what is identified just as a big cluster from a structural point of view. By analyzing it in more details, you find that there are two sub-communities discussing about completely different topics, and so this is something you want to know. Because you are completely losing this information if you're just looking at the structural part. I suggest you to go have a look at linkage.fr. It's something that can be tested online for free, and it's the implementation of this mix of natural language processing and graph theory. I'm going to be really, really fast, but the idea is that you can select how many clusters you want to look for, how many topics you want to look for, and it's going to propose to you the two axes of the analysis. So on the one hand, the structural point of view, and on the other, the subject that are the most discussed in each community that is found. So I leave the word to Aurélia again.
Once you've found your communities, an interesting analysis you want to make is who is the most important in my network. It could be for a marketing campaign or whatever. Let's say I'm a transportation network company, and I want to know, okay, this metro station should really be always okay, else it's going to be a mess in the whole network. It's really the type of information you need. But again, as for communities, there is no unique definition of importance. Let's say in this very small graph, which node is the most important? You could say this one, because he's really at the center. You could say this one, because he knows many nodes compared to the size of the network. There is no unique definition. There are actually different ways of measuring this importance, and they offer different truths about the node. For instance, on the left side, this node at the center is important because the two blue groups of nodes cannot communicate with each other if there is not this red node at the center. If we just cut this one, the two other groups cannot communicate anymore. This is the betweenness centrality. It says that you are on the shortest path of many nodes. So we must go through you to speak to many nodes. Another measure you can use is the degree. So on the right side, you are connected to many direct other nodes. So in this case, you know 4 persons, so you have a degree of 4. It's easy to understand, but it's really an interesting measure and really intuitive to understand. Another metric you can use is the page rank. It was used by Google for its search algorithm. And it will say that you are important because you know important nodes. It's kind of a recursion. And there are really various metrics, centrality metrics you can use, and most of them are kind of correlated. We will see that in 1 second. There are other metrics you can use. If you have, for instance, a directed graph, so I'm calling Alberto, there is a direction, he's calling me, there is another direction, or we are colleagues, there is no direction. In this case, you can define an in degree and out degree. You can also define the closeness. Are you close to many nodes of your network? For instance, this one is not that close with a step of 1. He just knows 2 nodes, but he's really close from other nodes here. As I mentioned, the centrality metrics are really correlated. However, as they provide different types of information, for instance, you can want to visualize the betweenness of someone and the degree or the page rank of someone and see a bit what is going on. Using, again, the Karate Club data, you can see here that there is kind of a rough linear regression between the page rank and the betweenness, and the persons with the highest betweenness also have the highest page rank. But you also can see some persons here that are not really bridges, but still they know important persons. So you can identify different roles in your network, a bridge, the leader, and so on, and try to identify hierarchies and understand a bit more what is going on. For instance, in your Panama paper network, you are really interested in finding connected groups and finding the intermediaries. A few words about the real life, so how can I do all that stuff? A few tools we think are interesting is depending on really the use case you have, the volume of data you have, and do you need to be real time or not, and so on. First, you have different analytical libraries. For instance, NetworkX is written in pure Python, GraphTool in C++, and iGraph in C. Both GraphTool and iGraph, I'm not sure about GraphTool, but iGraph for sure, have a wrapper for Python and R. So you can definitely use with R or Python iGraph. And Gephi is an open source software where you just click and you have communities in your network. So if you don't want that much programming, it can be useful. And personally, I would recommend iGraph because it's really efficient and it's really complete. I mean, all the community detection algorithms we mentioned are coded in iGraph. I will make a small demo. It's just one line. And it's quite efficient. If you like Spark, well, good news. There is Graphics. It's an analytical library for Spark and for graph analysis. The only issue is that not so many graph algorithms can be distributed. So it's a bit poor in my point of view. But still, you can compute a PageRank, find communities with a limited number of algorithms. So you can still make some things. And there are also different graph-oriented databases. So the most famous is Neo4j. But you also have different databases. In my experience, it was not always relevant to use a graph-oriented database compared to a standard SQL or NoSQL database, really depending on what you're interested in. For the shortest path and so on, of course, it's super optimized to do that, so it's really efficient. But for the use case I had, so more social networks analysis, it was not that relevant. If you also want to use some true data to test your algorithm, I would definitely recommend this website. So it's the Stanford Network Dataset Collection. You can find all these types of data, for instance, networks with ground truth communities. So if you are using some community detection algorithm, it can help you to say, okay, am I okay or not that much, and really help you in your implementation. You can also find Amazon product networks and road networks, so it can be really, really useful for you. Now I'm going to make a small demo with LinkedIn data and iGraph, so the Python libraries, to show you a bit how you can do in practice. So it's just a standard library, so you import it. You have specific graph data formats. In this case, it's, for instance, GraphML, but you have different types, but it's not that difficult. Here, with the function just summary, you can have the main information about your graph. So here you can see that you have 410 nodes, a bit more than 6,000 edges. And you also have node attributes. It's information on the nodes you have in your graph. Yep. Oh, better? Okay. So here you have some information about the nodes or vertices, the city of the person, the country, the LinkedIn headline, the industry, and a key. And here just I print a node, like the node 50, and you can see all the information you have. You can also easily plot your graph. So here it's a small graph, so you can easily plot it. And you kind of see that there is some form of structure. So here you have something. We can also measure the density of your graph. It's the number of edges among the number of possible edges. So here there are 7% of the possible edges that are actually in the graph. And in communities, intuitively, you will have a much higher measure. So, for instance, the most connected community would have 100% of the possible edges being actual edges. If you want to compute the degree of something, it's also very easy. So here you use the degree function, and you can save the degree information as a node attribute. And then you can, if you want, know who is a node with the highest degree, the highest page rank, or make a subgraph with only the most important nodes, or you can do really easily what you want. Here I use the walk trap algorithm, so based on short random walks. And you can, so it's super easy, community, walk trap, and it provides a dendrogram, so I have to cut it to get a final partition. And here I just select the optimal number of groups according to the modularity metric. So you have something. Seems to make sense. At least it looks good. But does it really make sense? If I take, for instance, this community, I can analyze the node attributes and just check what are the most usual countries and so on in this community. So, for instance, here you have mainly financial services, German, from Frankfurt. And with the headline, you can guess that they basically are colleagues working at European Data Warehouse, a Frankfurt-based company. So without knowing before the analysis this network, you can very easily understand what is going on. We can also zoom in the largest community, this one. This is a community. And just check the density. Here, 32%. It was 7% for the whole graph, so we indeed found a well-connected subgroup. And if we make a community detection again in this community, we can find that there are still some two subgroups. So it can be interesting, and yeah, one of them is a Quantmetry community. And the density is really high, so 63%. So at this point, we can stop the analysis because we cannot visually find another subgroup or something. To conclude, we we have written 3 blog articles. So unfortunately, they are in French, but if you want, you can go on the Quantmetry blog. We wrote an introduction to graph theory, community detection algorithm, and how to identify the leaders, so a bit more about centrality analysis. And if you have questions, this is the good time. And if you want to talk a bit about Quantmetry, well, afterwards we can, just take a coffee and so on. Thank you.
Thank you.
If you have questions on the practical implementation or the algorithm, well, don't hesitate and else, yeah.
First, thank you for the presentation. Just one question. You said that the dataset from Panama Papers got 1 billion, something like that, very high number.
Mm-hmm.
And your tools to manage that, how did you manage it?
We didn't. The international consortium did.
Okay.
We just thought it was interesting to show in the real life what can be done. But they used Neo4j, and it has its own language, Cipher. It looks like SQL, kind of. So you can easily request search information. And then they used database software. But in my personal experience, I was more in this situation where I was having a few millions of nodes and like 100 million of edges. So it's okay with a good computer.
Just to complete, there are 2 possible ways to deal with it. The first one is to pre-select something that is more interesting to you. This can be done. The other thing is that I believe that in the end they use mainly local approaches, because local approaches, I mean, the degree you can find the degree of a graph with 10 billion nodes is not a problem, because you're looking just at one node at a time and at its own environment. On the other hand, if you want to calculate the betweenness, for instance, it is I totally believe that they were not, even with very very powerful machines, they were not able to find the complete betweenness of these graphs, because you have to study all the network at the same time. And this is completely unaffordable. I mean, we are able to get up to 500 nodes, maybe with more, it's exponential, so with a more powerful machine, you can get to 1,000, 1,500, but you are not going much further than that, because it's really exponential in the number of nodes and in the number of links. So you have to look at the graph locally, mainly.
Okay, thanks.
Thank you.
Thank you.